So good afternoon, everyone. I'm Helen Rosenfeld. I'm the Executive Director with the Massachusetts Science and Engineering Fair, and thrilled to have you participate in today's middle school session with Marianne DiMaria. She's a teacher at Millbury Junior Senior, I just got it wrong, Junior Senior High School. I got it right. And this has been part of a series of workshops that we're doing to help people prepare their students for science fair. So thrilled to have you today, and I will turn the floor over to you. Thanks so much.
Hello, everybody. So I'm going to share my screen, and so you can see the presentation and what else I'm doing on there. And let me just get to the presentation. It's right here. Forgive me. Let me get rid of me. Okay. Can everybody see that? Helen, is that clear to everybody, or? I hope.
Yes,
Okay.
absolutely.
Okay. So maybe I'll put some of this back on so I can at least see people's faces, or maybe I'll minimize it. Just shout out if you can't see something. So welcome to today's workshop on November 18th, 2020. And today, well, we already did introductions. Thank you, Helen. And I think we went through these slides last week, but for new people joining with just watching this video, these are our middle school regions and the chairpersons, the people that are head of the committees in each region. I don't know, I can't talk today. This is the date of our 2021 middle school fair, and it's a virtual fair this year for the state. So this is the state fair, not the regional fair dates. Those will be announced later. So today's workshop is about analyzing data and drawing conclusions. So I was lucky to do a workshop a couple of weeks ago where we looked at developing a hypothesis and writing your procedure. So this presentation follows directly after that. Okay, so what do we do with the data we collect, right? So what we have to do with the data is we have to organize data, we have to analyze the data, and from that, then we draw some conclusions. And I put CER question mark here. Do you guys, does anybody know what that means? When we say CER, you can just shout out. I can't see people. I'll try to put this back on. Do you guys know what I mean?
No, I don't.
So it means claim evidence reasoning. So I put that there as a question mark because even I'm starting to change, trying to get my conclusions to follow this format, the claim evidence reasoning format. So I'm going to leave us up on the screen for as long as I can so I can actually see people. So from the last week, it was, I guess I can't do that. These were the scientific questions we asked. We had 3 sample experiments. How does the temperature of water affect the rate of a chemical reaction? How does the amount of salt affect the number of seeds germinated? And then our third was a physics one. How does the height of the drop, or how does drop height affect the bounce height of a golf ball? These were the hypotheses we stated. I wrote them down. I don't know if you guys remember a couple weeks ago, you guys stated these hypotheses, and I just wrote what we said. So notice that when we state a hypothesis, it's stated like a trend. It's not like at this temperature, this is what's going to happen. It is, if the temperature of the water increases, then the rate of the chemical reaction is expected to also increase. And then you would explain this is expected because. And then the same thing with the salt experiment. If the amount of salt in solution increases, then the number of germinated seeds is expected to decrease. So we always try to state a hypothesis as a trend. And so I wanted to bring back our questions and our hypotheses so that we can then, the data kind of make sense to new people joining us. And then the last one was, if the drop height decreases, then the bounce height of the ball is expected to also decrease. Okay, so here's some data. All right, and these data are already organized. So when I say organize the data, oh, I just put the variables back there. So this was our chemistry experiment. Our independent variable was the temperature of the water. That's what we changed on purpose. And we were measuring the time it takes for the Alka-Seltzer tablet to dissolve. So when you organize your data into tables, these two variables need to be your headings for either your columns or your rows. And if you teach kids that, then it helps, it helps them when they go to organize the data. So these are actual data from a student that did this experiment for me a few years ago. This is their science project data. It's not perfect. So I'm gonna escape out of here and go into, I have it in a spreadsheet. So hopefully you guys can see this now. Does anybody have any questions before I keep going? Now I am gonna put you guys on there. We still good? Okay.
And if you do have questions, you can also put them in the chat and then I can field the questions as we go if necessary.
Thank you. So here are, I put this as sample data, and I could link this, or yeah, I could link this to this presentation so you guys could have this too, because this is a copy. This is actually the students' original data, and then here's the copy. So I didn't take a picture, but I don't think I have this one, but in the lab notebook, the data do not look like this. And I know Lisa did the first presentation with setting up the lab notebook. So when kids are collecting the data, like in a notebook, the data should be like not really organized. Just they put the date at the top, and they're collecting. They're doing cold, room temperature, hot, and then repeating trial 2, cold, room temperature, hot, and they're just writing numbers down in their notebook. So when they go to organize the data, now thinking of how to set up a table is hard. So that's where I try to always get them to think of their independent variable will create, will be the column headings, okay? So here's what they changed on purpose, the temperature. And we have 3 levels of an independent variable here. So here's your cold data, here's your room temperature data, and here's your hot data, okay? And then they said test number. I would normally do trial there, like trial number, and notice the amount of data they collected. So all of these data were not collected in one day. Like if you look through the notebook, it was page after page after page. And probably in one day, they were able to do maybe 5 trials. And remember what we talked about, like in procedure, that they wouldn't have done all the cold in one day. You have to do it like cold, room temperature, then hot, cold, room temperature, and hot. So they're pouring through their notebook, trying to find all the cold data. And then when they're doing this, they're putting those numbers into this spreadsheet or into this Google Sheet. And then the same thing for the room temperature data. They're putting these numbers in, they're finding them in their notebook and then organizing them in this way. And here's where the first errors can come in. So can you guys tell me, what do you think is a common error that students do when they're organizing their data like that, going from the notebook to the spreadsheet? What do you think? You guys can just shout out if you want.
I'm just thinking here.
So they're like, pretend this is the notebook, this piece of paper. And so I'm a student and I'm pouring through, I'm trying to find all my cold data.
I think sometimes what they might do is just, just give all the coal all at once.
Correct. And go ahead.
do
I'm
the
sorry. I
room
keep
temperature all at
interrupting you.
once. They really haven't set it up. They just.
So where I was going was more, when you copy numbers from one place to another, even kids, they make mistakes.
Well,
So it's really, right, just copying from a notebook to organize into a table, mistakes will be made. That's where like a lab partner or getting kids to hook up and help each other, even if they're not partners, like where one kid will read from the notebook and the other kid will input the data. When I was even a scientist in the lab, I cannot tell you how many times I made mistakes inputting data, going from the lab notebook to the spreadsheet. So it's really important that like the kids go slow at this part, and while they're looking for all their data in the notebook, that they just go slow and put it in slowly, or go across like one at a time this way. But double checking and triple checking inputting data is important, I think. But also what you said, Sister Jean, was like, don't do all of these in at once, because there's going to be variability in your classroom or work or in their home with temperature. Every day slightly different. So you want to make sure you go across this way. Okay. That leads me to another thing. Kids like to, do your students just immediately go to the spreadsheet? Like they want to set up and just put the data right in here because they're so tech savvy now. And it's really important to get them to just record the data into a notebook first, because that like gives good habits of that documentation piece. Because I've had some kids just do all their data in a spreadsheet and then they go back and copy it into the notebook, and that defeats the purpose. That's just a waste of time. And the idea here is that, they should not be collecting all the data in one day. It should take a couple days or a few weeks to collect data for a science project of this magnitude. So,
I often have the students do entry dates when they actually do the 3 variables. You do them once, and then if you do them 5 trials, next time you put in the next date that you do this, so that I can see some kind of sequence of when
absolutely.
and how long it took them to do it.
That's a great point. So dating, and this is one, so you don't see the dates in this data table, but if you saw this student's notebook, it would have had the dates in, and that's the key point. You are absolutely correct, because you want to see that they didn't do this all in one day, and that they, like, maybe they did the 5 trials in one day, and you could have then, let's say, 6 different data tables if they wanted to, instead of one big one. But then you'd have 6 different graphs, and that becomes very busy on a display board. So at some point they do have to organize all. I would recommend that they organize it all in one big table. But again, that takes, them like synthesizing all the data into one place, and mistakes can be made there. The other thing with these kind of data is, like, notice the time is, make sure that, like, if they're doing any time data, it's all in the same units, because sometimes like stopwatches will do minutes and then seconds, and they've got to convert all of that to just one unit. It's either going to be minutes or seconds, but not both. So these data are all represented in seconds. Okay. All right. So let me ask you guys another question now. So now the kids got all the data into this table. So they've organized it really well. Now the next step is to analyze the data, because we want to know if the hypothesis was supported or not. So that's where the graph comes in, to make the data easier to understand, because looking at all of these numbers, nobody in the public wants to see all these numbers. And it's the job of the student and as a scientist to take all of these numbers and reduce them into some type of graph that makes the data easier to understand, so we could say whether the hypothesis was supported or not. So what do we do with these kinds of data? Like, how does the analysis begin? What do you guys recommend for your students? What would you do with it? It's kind of at the end here too.
Yeah. Well, first of all, doing the spreadsheet is a good thing to show. I would probably, go back to the hypothesis, and based on the hypothesis, I would look to see what I have. Now, this is just the spreadsheet. I haven't even graphed it yet.
Right, we haven't graphed it. I guess that's what I'm asking. Like, so let's just do this. Watch what happens. This is what some kids like to do. They'll grab all these data, and then they'll just go right up to the little graphing or the chart icon, and something really ugly is going to come out of here. So we have, like, kids will just give you these kinds of graphs. They'll say, oh, well, here's the graph, because they'll just take whatever Google Sheets pumps out at them. And this makes no sense. because what I tell my students is, okay, your job is to make all these numbers easier to understand, not harder. And this gives me a headache. I can't even, while it looks pretty with the cold line, the red line, and the yellow line, and maybe it could give, some sense of variation within your numbers. I guess that could be good. I really just want, what I try to teach the kids is, normally on your x-axis should be your independent variable. And on your y-axis should be your dependent variable. So I don't want to graph all these numbers. I only want to graph these final 3 numbers. So I encourage kids to take the average. So do you guys know how to do that in the spreadsheet? You just go up here, you say average, and you select all the numbers. We'll just go up, that you want to average, and then you just hit enter. And so there's the average for our cold water. Here's the average for our room temperature water. And then here's the average for our hot water. And then how do we graph that? Well, if you just grab these numbers and you say, okay, we're going to go to the graph, you get those. I can change this. I could say, I'm not getting what I want here. This is like a histogram and I get 3 bars, but that's not really what I want. So what I want is, I want my independent variable, the temperature of the water, on my x-axis, and I want that average time, average reaction time in seconds on my y-axis. So what I tell the kids to do is they actually have to create a second little data table down here. And so there's my independent variable. And then I'm going to just type in average time for tablet to dissolve. Okay, so I'm making it really explicit, and I'm just going to wrap that text. And I can't copy and paste these. If I do, I'm just giving you some, oh, it did. Notice how I've got funny numbers, because it's looking for a formula, and it's actually including this, I think, in the average. I don't know what it's doing, but I want to actually type in 203.22, 70.50, and then 22.99. Okay. And now I'm going to grab these 3 numbers. So I've taken 100 pieces of data and reduced them to just 3 numbers. And that's what I'm going to graph. I don't want a pie chart. Doesn't look good to me. I want that bar chart. And if you notice now, because we made this second little table and we put in all the, we kept all of these, we put in the writing that we needed to do, and I put that in, it already gave us our y-axis label, and it labeled the 3 bars for us. But we're not really done here, okay? So I've got to go customize. I'm going to edit this chart. I'm going to customize it, and I want to put in a title. So I'm going to say effect of water temperature on average time it takes, on average time for tablet to dissolve. And then I'm going to change that. I'm going to put in a title here, and I'm just going to say water temperature, and in parentheses, degrees Celsius, because I don't feel like getting the little degree sign right now. So there's my x-axis label, and each bar is also labeled, and there's my y-axis label. So now I have my independent variable clearly labeled there, and my dependent variable clearly labeled here. So now I think we're done organizing, and like you said, Sister Jean, the analysis, because now we've created a graph. And now can you see the trend? We could actually add a trend line in here. Do you guys know how to add trend lines in? No, I want customize series. I can add a trend line, and there's my trend line. So what does this trend line tell us? Normally you do that with like scatter plots, but I can still put a trend line in here. So what does that trend line tell us? Anybody want to take a guess, or do you know?
Well, it's descending.
Correct. So so we could talk it out. As the water temperature increases, what happens to the time for the tablet to dissolve?
Takes less time.
There you go. It takes less time. So the reaction is faster. And notice we were smart when we organized our data, that we did it in order of cold, room temperature, hot, so that we were able to put that trend line in. If a kid graphed like room temperature here, cold, and then hot, we wouldn't have been able to use that trend line in our graph. The other thing, do you guys know how to change the color of the bars? They let you change, like Google Sheets didn't let you do this before, but now you can change individual bars to match like your little data table there. So this one will make white, and then this one will make red. And now we have bars that the white doesn't look good. I guess we need to change that to a different color, make it a little grayer. So now you can actually make your bars match your data table, and then everything looks pretty on a display board. Are there any questions before I move on? Does this make sense?
Well, this makes a lot of sense. Thank you. It's well done. Yes.
Okay, so now I'm going to go back though to our hypothesis. Where is it? What did I do with it? So here's the hypothesis for this one. If the temperature of the water increases, then the rate of the chemical reaction is expected to also increase. So I'm just going to move this. Do these data support or reject that hypothesis? So they support it, right? As the temperature increases, the rate of the reaction also increases. And by that, we mean it takes less time for the tablet to dissolve. It took 20 some seconds on average here, but over 200 seconds on average here with the cold water. Okay. We good? Can I move? So the other two will not take as long for us to go through. Please stop me at any time. So remember the biology experiment? That was the salt and the seed germination experiment. So these data are actually from one of my cohorts this year, okay? So this is how we set up this data table this year. So you can see what's different between this one and this one. Notice the independent variable was our column headings here because we had all the trials. But in this one, the independent variable is over here. So it's kind of like the row headings because we were tracking seed germination over time, okay? So we put in our seeds, and then we had 0 seeds germinating, and we did it in duplicate, dish 1, dish 2. And then we looked at how many seeds were germinated by day 4. And they had 10 in each of the dishes, and then 5 and 6, and then 2 and 2, and 0, 0. And we ended up taking an average and then calculating the percentage of seeds that germinated. So in the end, this is what we graphed. But again, when we graphed these data, we did not select all of this. So I can go back to a spreadsheet, but we had to make, just like we did here, where we made a second little data table, we did the same thing here. I don't know what I'm doing. We did the same thing here, where we pulled this out and we pulled this column out. So here's our independent variable. We changed the amount of salt on purpose, and then we calculated the percentage of seeds that germinated on day 4. And this is one of my students' actual graphs. So there are some errors in here. I would have said percent germination on day 4 here. And then this is correct amount of salt. The title looks correct, effective amount of salt on seed germination. again here, so how does the, like, was the hypothesis supported or rejected here? Or we could put in a trend line too here, and what would that trend line say? It's again, same thing, a decreasing trend line. So as the amount, you guys finish the sentence, as the amount of salt increases, what happens to the percentage of seeds that germinate? Oh, I can't hear you, sorry.
It decreases.
It decreases again. So remember, Sister Jean, we were talking last week about like how to state hypotheses. So this is where I wouldn't have my kids say at 0%, I think at 0% salt, I think 100% of seeds would germinate. I would just have them state the trend, okay? And then see if your data and a trend line supports the hypothesis. Finally, the physics experiment. Now, these are actual data from one of, I don't know, I think this was, we actually did this in 7th grade, and I don't know what kind of balls we used, whether it was golf balls or not, but these were the real drop heights, 100 centimeters, and they wrote them in the, reverse order, but that's okay. And then every group, like different groups of kids, this was before COVID, so we were able to actually work in groups together. And then so there were 4, what?
It's difficult now because we can't have them work in groups.
No, and you have to, like, even using rulers is an issue because I have to wash everything, so, but now notice the same thing, like we take averages, and I did put on this separate little, oh, I keep doing that. I did put on the separate little, eventually we just graph these data right here. So this is not, this is like lab, like within a classroom, this isn't a science project. So you wouldn't have this problem with a kid doing a science project, but they would do like trials, like there would probably be, 1, 2, 3, 4, 5, like 20 trials of each one, like, so 20 times bouncing the ball for each one of these, and then they get their own averages over here. But again, here are the data, and again, the perfect trend line came out of this, that as drop height decreased, I guess. So see the data, they go the reverse way here, 180. So maybe we go this way. As drop height increases, so does the average bounce height increase. Or you could, do it the other way. Okay, so that is organizing and analyzing data for projects. Before I move on to writing conclusions, does anybody have any questions?
No, this is good. Thank you.
Oh,
Well
you're
done.
welcome. And spreadsheets, good. All right, so now the conclusion. I have simplified, this is a very like the conclusion's very simplified here. So in paragraph 1 of a conclusion, I have them state whether the data support or reject the hypothesis. So that's their claim. So now we're connecting to claim, evidence, and reasoning. So that's the claim. What exact data are used to support your claim? So if you're saying the data support the hypothesis, or the hypothesis is supported by the data, or the data support the hypothesis, what exact data are you using to support that claim? And then you also have to explain how the evidence supports the claim by connecting to the science concepts, and that's your reasoning. So anybody doing claim, evidence, reasoning, it's kind of embedded right in your first paragraph. And where I've simplified is the second paragraph. Like paragraph 2 for me was always, what are some possible sources of error? And then how could you extend this experiment further? Like now that you've got this answer, what could you do next? I kind of cut that out a little bit for this year, but I intend to always put that back in future years. But here are some examples. So this was the conclusion written for this student when they did this chemistry experiment, the Alka-Seltzer project. So we could just read this one out loud. So here's the claim. The hypothesis was supported by the data. As the temperature increased, the average time for the tablet to dissolve decreased. Okay, so that's our claim. We're saying the hypothesis was supported. Now I've got to back that up with some evidence, and here's my evidence. Oh, I actually said this. This means, or the kid said it, this means the Alka-Seltzer chemical reaction was faster because with time, smaller time means faster. So, and then here's your evidence. The average time for the Alka-Seltzer tablet to dissolve was 203.22 seconds, 70.5 seconds, and 2.99 seconds for the cold room temperature and hot water, comma, respectively. I teach my kids this word, and that's why I don't have them rewrite it every time. And I explicitly teach what this word respectively means. And that means if you have a list here in order, it matches this list in order. So they actually learned this word early on for me. And then here's the explanation. So there's a claim, first sentence. Here's the evidence, this sentence. And then in this chemical reaction, the solid Alka-Seltzer tablets need to be in contact with the liquid water according to collision theory. And they would have done some research on this. The greater the temperature, the faster the molecules move. At higher temperatures, the water molecules are hitting the solid tablet with greater force because they are moving faster. This increased force causes, they have a typo here, the tablet to break apart faster, or cause the tablet to break apart faster. A couple things here. Number one, you'll notice there's no I's, me's, we's. So I don't know how you guys feel, but in science, we always encourage the kids to write in passive voice. That's tough for them, but try to encourage them to do that. And then I hope the claim evidence reasoning was clear here. This was all reasoning, the connection to the background information or the science concepts that explain why this happened. I would have liked to have seen this student expand a little bit more on the evidence. For example, if I took 203, what I try to encourage my kids to do is take take the numbers. So this number 203.22 is 8.8 times larger than the 22.99 number. So it takes 8 times longer for the tablet to dissolve in the cold water compared to the hot water. Or they could say it the opposite way. It's 8 times faster. So I would always like a second sentence just to drive that home to the reader that this is really good data. This is really showing you that the data support your hypothesis. Any questions there before I move on?
This is excellent. Love it. Thank you.
Okay, thank you. And then, so see how the second paragraphs have gotten really minimal. So possible sources of error include not timing the reaction accurately because of difficulty seeing when the tablet was totally dissolved. My students like to make stuff up. There's really sometimes there's very few errors. Errors are always in measurement, not usually, not measuring something accurately or precisely, but they like to say, not putting in the exact same amount of water. But the second paragraph should be a little more detailed. There should also be maybe where else can we go from here? So I just wanted to point that out. Okay. The next one is exactly the same, only even more minimal. I don't know how to say that. So this was a conclusion directly off one of my students who did it this year, one of their lab report templates. So again, claim the hypothesis was supported by the data. As the amount of salt increased, the number of germinated seeds decreased. The number of germinated seeds for the 0, blah, 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 was 10, 5.5, 2, and 0 respectively. And then they give the percentages. The percent germination for blah, blah, blah was and the same thing. Again, I told you, I teach my kids this word early on, respectively. Again, I would have liked them to say, this is almost double the amount, the percentage here, but they don't. And then this is not the reasoning is not extensive here. The salt caused less germination because the salt traps the water and prevents the water from getting to the seeds. So this is more about like adhesion and cohesion, like the water molecules being attracted to the salt. And if they're attracted to the salt, they're not going to be accessible to the seeds. And again, same thing, not, putting in the wrong salt solution or not counting the number of seeds correctly, germinated seeds, because it was difficult to actually tell when the seeds germinated or not. But they didn't say all that here, but they should have. And finally, same thing with the physics conclusion. It's the same exact format: claim, evidence, reasoning, and then possible sources of error. So that is it for this presentation. So questions? I know this one's a little shorter. I don't know.
Well, you know what? This was very concise. I really enjoyed it. I like the word respectively, and I am going to include that. I never have the students say, if my hypothesis didn't work or anything like that, based on the data. I always say based on the data, this supports the hypothesis, whatever. But I love the way you set this up. This was excellent.
Thank you. Any questions on spreadsheets or the Google Sheets? I used to call myself the Excel queen, but I was bumped off my throne by a few of my students, actually. So I can't call myself the Excel queen anymore because of all my experience in the lab. Was not that I'm arrogant, but I love Excel. I love spreadsheets, and I like trying to figure things out with them. So if you have any questions about Google Sheets or Excel or anything, please let me know. My email. My email's on here somewhere, right there. But also, this is a link to that handbook. If you hadn't seen it, click that link when it's shared out. Well, let me just show you that while we have a couple minutes. Do you mind? I know I ended early. So this is like a handbook again. It was written years ago, but it's been changed. And these dates don't match because I didn't update it for this year yet. But I'm going to scroll what we were doing. My computer's slow, I'm sorry. I don't know, won't let me, oh, here we go. It's probably loading and I'm scrolling at the same time. So we're past materials and methods. Data collection. Okay, so I love, I harass them with this. So when I teach them, when they start collecting their data, I say you need to begin collecting data immediately because you need to have, 100 to 200. If you have experimental problems, you need to make time because you need 100 to 200 people. If you have trouble getting materials, you need 100 to, if it's your birthday, you still need to be able to collect. So we go through that like verbatim and I make them read that out loud. And then what we did today was not the data collection, but we did this. So we did organizing the data, analyzing and writing like, an abstract, and then final copy of the written report. So that you guys have access to all of that. And you could tell like, oops, I don't know what I'm doing. Like my voice is in a lot of this document. But can I stop sharing my screen now, Helen? Do you mind? So I can see people. So,
Fair enough.
Are there any other questions?
Just, are we going to have that submitted to us or?
Yeah,
Because this is
so
actually-
like the other times,
this
we'll
is-
send everything in an email, and then we'll also post this video if anyone else is interested on YouTube.
And you guys, the people who asked me to share, like you guys got it okay. I shared, okay, good. You notice I share view only and then you just make the copy. Okay, all right. Of the documents. Okay.
Any other questions before we wrap up?
Very good. Thank you very much.
Yeah, thank you, Marianne. That was awesome.
You're welcome.
Just
Thank
you're so great at getting to the point and sharing how to convey this to your students.
Yeah, I could have gone on and on about spreadsheets. But I hope the 3 examples will help people enough to, and just make sure that the conclusions are a little more extensive. They were really concise for this presentation, but I think teachers will figure that out and know to beef those up a bit. Okay. All right.
Fantastic.
Thank you.
Well, thank you all for participating, and thanks again, Marianne.
Bye.
Bye, everyone.